Swayam Prabha. Digital India. Educated India.
We are back into our lecture series on advanced hydraulics. Today we will start the module 3. The module 3 is on varied flows. So, if you recall that, as we mentioned, we are today going to start on the third module. If you recall back the first and second modules, in the first module you had briefly gone through the open channel flows. What are the various open channel flows? We have also described about the critical flow. We have also described about the subcritical flow and supercritical flow, various aspects on the general open channel flows. These things we are described in the first module. In the second module, we discussed on uniform flows. What is uniform flow assumption? How we can assume uniform flow in various natural conditions? What are the process to analyze uniform flow? All those things we had discussed. We have discussed about the design aspects of uniform flow also in some of the things. If you recall, especially in the last class, till the last class, we discussed on the uniform flows in open channels. They have constant depth and velocity throughout the reach of the channel. That is what is meant by uniform flow. So, but now if you look into the aspect now seriously, as you have covered 2 modules and now you have gone through various field conditions, you might have already gone through the field conditions and all, you may see that the uniform flow approximations are not that suitable for many of the natural processes. So, what should be done? We need to understand the non-uniform flow mechanisms. So, many of the non-uniform flow, they are called varied flows. So, this module deals on the varied flows. So, what are the various types of varied flow, or what is meant by varied flow and all? So, that is generally the non-uniform flow in open channels, they are called varied flow. You may encounter several type of non-uniform flow. Some of the cases you might have seen how, if you construct a dam, from the spillway the water splashes out to the downstream. This is a particular type of non-uniform flow. We will discuss on what is that category of non-uniform flow called. That lecture in the later part of this lecture, in this lecture series we will discuss on those things. You will see that if there is any block in the flow path, the water in the upstream gets rise, a wave may get generated. These things are also non-uniform flow. So, we will deal all those things. So, non-uniform flow mainly based on how the uniformity of the flow condition varies with respect to space as well as time. That is the way we consider non-uniform flow, especially if the flow varies with respect to time, you know that it is called unsteady flow, and if it varies with respect to space, it is called distributed flow, or in hydrology, especially in hydrology courses and all, one might have already studied distributed flow, lump flow and all. So, these things we will see according to our course structure and all, how to study these non-uniform flow mechanisms, how the flow may vary with respect to space or with respect to time or with respect to both. So, there are mainly 2 types of varied flow, that is gradually varied flow and rapidly varied flow. So, we can in general call them varied flows, both of them, how the flow varies gradually with. So, here let me inform you, the varied flow we are considering the space variable. So, it is not the temporal component that is being taken into account. So, this in this space variable, so how the spatially the properties of the flow, that is the depth of the flow, the velocity of the flow, all those things, how it vary with respect to the space. If one travels from upstream to downstream, these properties of the flow, if it varies, that is a non-uniform flow. And in this non-uniform flow, there are two main categories, that is gradually varied flow and rapidly varied flow. So, two varieties are there, two types of non-uniform flows are, two types of varied flows are there. In addition to that, if the flow varies with respect to time, that is also taken into account, and those category of flows are called spatially varied flow. So, I have not written it here, but those quantities are also coming into picture in general open channel flows. So, we will begin with the gradually varied flow. So, we can give in a short GVF also. So, here onwards, wherever if I give this abbreviation GVF, it means the gradually varied flow. So, gradually varied flow in open channels, it is a non-uniform flow as we mentioned earlier. The flow aspects like depth of flow, velocity of flow. So, especially these two properties, they changes gradually along the reach of the channel. So, if you have a certain reach of the channel, then it may gradually change the depth of flow. Say here the depth is y 1, here the depth is y 2. So, as it proceeded from upstream to downstream, a certain distance when it travel, the depth of the flow is getting reduced. So, this is a gradually varied flow. So, that variation in the depth of flow is gradual. Similarly, the velocity, the change in velocity of the flow is also gradual. So, it is not happening all of a sudden and all, therefore, it is given by the name gradually varied flow. Gradually varied flow has certain assumptions and all, we will come into those things, and precisely though for those reasons only it has been named as gradually varied flow. A question I like to ask to you is, why is the flow called gradually varied? Why is it called gradually varied flow? If you have specific answers or if you know the things about that, you can please tell them. So, the flow aspects, as I mentioned earlier, it changes gradually. So, even a layman, he may not be able to witness the change in the flow aspects, that is the depth of the flow and velocity of the flow and all, the changes in that considerably between one section to another section, that cannot be seen. So, it is varying only gradually. Therefore, many of such flows are called gradually varied flow. So, I can just give in a figurative way, say the depth of flow from initial to this thing, it is gradually varying after a certain traverse. This is y 2, as it, this is a particular type of gradually varied flow. You may also see a gradual increase in the depth of flow. So, such type are also witnessed in many of the open channel conditions. So, they are all due to the change occurring gradually. It is generally called gradually varied flow. Moreover, if the depth of the flow, if it is decreasing as it flows from the upstream to the downstream, then the surface of the water, that is the water surface profile, they are called drawdown curves. If the water surface, if it is increasing gradually as it flows from upstream to downstream, then the water surface curves are called backwater curves. So, one can easily understand those things, the meaning of this thing. So, we are not going to further discuss on the language of those terminologies. Next question I would like to pose in front of you is, where do you see gradually varied flow? Where do you see gradually varied flow? So, if a dam is constructed on a river, for example, let me just draw a river bed, you are taking a considerable reach of the river. Say there was a uniform flow initially in the river was having uniform flow. Suppose if you construct a dam now across this channel. So, initially the flow surface, the water surface was of this form. Now, due to the dam construction, you may see that there is a gradual increase in the water surface. This is a backwater curve. This is, you can see gradually varied flow. In this case, the depth of the flow is gradually increasing as you move from upstream to downstream. One can also see, for example, in the same type of uniform flow, a channel, if it is having uniform flow, suppose if it is witness to some sort of sudden drop in the bed of the channel, say the bed of the channel, it can suddenly drop. You may have seen some step channels and all, where the bed just drops in a step form and all. So, now the channel was already having a uniform flow. Now, due to this drop here, you may see a gradual reduction in the depth of water like this. Then it will flow like this. So, this portion, this is also a gradually varied flow. It is also a gradually varied flow phenomenon. So, you can see gradually varied flow in such situations as well. So, these are some of the two classic examples where gradually varied flow are witnessed. What are the assumptions involved in gradually varied flow? Let us enumerate some of the assumptions in gradually varied flow. The premier one of the most important criteria is the gradually varied flow is steady. I mentioned earlier, you can have varied flows with respect to non-uniform flows with respect to space as well as time. So, here the flow is not varying with respect to time, it is a steady flow. Still, as it is varying with respect to space, therefore, this term it comes under the varied flow criteria category, and the parameters are changing gradually, therefore, it is gradually varied flow. So, gradually varied flow, it is a steady flow phenomenon. Mostly we consider the hydrostatic pressure distribution. So, inside the channel, say if the channel bed is like this, the flow profile is like that. So, as you go by depth, the hydrostatic pressure phenomenon is valid here. That is, the pressure increases with respect to depth from the surface of water. From the surface of water, as you go down, the pressure increases in a hydrostatic way. So, that assumption is true for the gradually varied flow. We assume that the slope of channel is small. We assume the slope of channel is small. We are also considering the channel as prismatic. That is, the channel is not changing its cross section as we proceed from upstream to downstream. So, that prismatic condition has to be maintained. We are also suggesting that roughness coefficient is same. Roughness coefficient, it is not varying with respect to depth of flow. It is constant for the problem. So, based on these assumptions, one can start analyze the gradually varied flow. So, as this is a postgraduate course, we will be trying to analyze it in a more rigorous, in a more philosophical way, or you have to use the general equations that are holding good in any of the physics. So, those things you have to apply here in the gradually varied flow and try to analyze them. So, let us see the conservation of equations, the conservation equations for gradually varied flow. What are the basic conservation equations? Conservation of equation for mass, conservation of equation for momentum, conservation of equation for energy, then conservation of equation for enthalpy and all, it is there. However, as we are dealing with open channel flow, where the flow is predominantly incompressible and all, the conservation of enthalpy and all we are not going to consider here in the syllabus. So, the conservation of mass, momentum and energy. Let us see how these equations, how these property or how these principles are applied in the gradually varied flow. So, if you recall the uniform flow, in the uniform flow also we had developed some fundamental conservation equations, especially while deriving the chassis equation and all, we had suggested the fundamental conservation equations that can be used. So, there we applied for the conservation of mass from the continuum approach. If anyone who has studied continuum mechanics, or if anyone who has studied fluid mechanics, hydrology, all these courses and all, you might have heard about the equation Reynolds transport theorem. So, this we have already informed to you, means we have already covered this portion. Reynolds transport theorem briefly we have informed about it in the module on uniform flow as well. So, again I am repeating it here, the Reynolds transport theorem. Reynolds transport theorem suggests the material derivative, that is the material it is from the Reynolds transport theorem one can develop many conservation equations. So, the Reynolds transport theorem RTT, it suggests that the material derivative of any extensive property B, capital B. So, I am denoting the material derivative as capital D by dt. So, this material derivative of this quantity is nothing but the time rate of change of that property stored inside the control volume plus the net outflow of that extensive property across the control surfaces of the volume. So, now you may be confused why I am using certain terms called control surfaces, control volume. Control means extensive property, intensive property and all. I have used those terms here in this equation. What do you mean by those things and all? Control volume, you can just suggest, say, if I take arbitrary shape, any arbitrary, here I am just taking a rectangular box of dimension del x, maybe del y, del z. If I take such an arbitrary shape, now this shape can be incorporated in any volume or any of the continuum you are taking into account. Your fluid, your water, which is a fluid, I hope you know it is a continuum. Most of the analysis on water is based on the continuum approach. So, it is a continuum. So, if you take any arbitrary volume of the water, so if you have a specific size, specific dimensions for those things and all, then based on the continuum approach, you can suggest that volume as a control volume. You can also infer that any property, extensive property on that control volume. So, that material derivative of that extensive property is nothing but the time derivative of the net extensive property generated or lost inside the control volume plus whatever outflux of the outflux, that is net outflux, both in outflux as well as influx is being considered here, of these extensive properties across these control surfaces, they are also coming into picture. So, one can easily denote that when you consider the channel reach in the gradually varied flow, when you are taking the two sections. Now, these two sections, the volume included within these two sections, you can consider it as a control volume now. So, whatever mass, or if the extensive property, if you are taking it as mass, or if you are taking the extensive property as momentum or energy, whatever extensive property, that material derivative of that extensive property in this control volume is equal to the amount of extensive property generated inside this control volume plus whatever movement or whatever quantity of this extensive property is transferred through the control surfaces of this control volume. They have to be related. So, that way we are now going back into this thing we had clearly discussed in the derivation of Chassis equation also, if you remember them. So, the same property now we are going to apply in the gradually varied flow. So, here the channel reach is being taken, a control volume is suggested. So, you can have the cross section in the upstream like this, in the downstream like this, you may have them, whatever be. So, in this control volume, the Reynolds transport equation, if you use them, so, please note that here velocity has been represented in a vectorial form. V dot n that is it suggests the component of velocity in any of the plane surface, any of the surfaces of the control volume, that is any of the. So, along that surface, that is across that perpendicular to that surface, how much amount of that flux is coming out, that is being suggested by this quantity V dot n. So, that you have to try to infer them. V is your extensive property. So, extensive property that are related, the properties that are related with mass, if you recall them, that is given by B. Small beta is the intensive property. Then you have volumetric integral as well as the areal integral. So, if you apply it to the control volume of the fluid in the gradually varied flow phenomenon here, you will see. Let us start with conservation of mass first. Let us start with conservation of mass first. So, your extensive property is mass. Therefore, the material derivative of mass is 0. I hope you understand them. Mass can neither be created nor be destroyed. The intensive property m by m is equal to 1. We are considering incompressible fluid. So, rho, it is not going to change with respect to space as well as with respect to time. So, you have your Reynolds transport equation as dA. Now, very simple thing. There are two terms in this equation. On the right hand side, there are two terms. So, the first term suggests the total rate of change of mass stored inside the control volume. It is the total rate of change of mass stored inside the control volume, and this quantity gives the net outflux of the mass. The net outflux of the mass of water across the control surfaces. Of the control volume. Now, recall the assumptions given in the gradually varied flow. So, as we have suggested, the flow is steady. So, definitely you can see that this quantity can vanish. If the flow is steady, this quantity vanishes. So, you can now easily suggest the net outflux of mass across the control surface of the volume, control volume is equal to 0. What does this mean? As we have suggested, the water liquid considered in the control volume, water is incompressible. So, this is nothing but V dot n dA. N is the unit outward normal vector of any control surface you are taking into account. So, V dot n is the component of velocity of water that is perpendicular to the plane of the surface which you are going to take into account. So, if you expand this thing, we are dealing with one dimensional flow. As mentioned in the beginning of this lecture series itself, mostly the river flow or channel flow, they are one dimensional in nature. That is the predominant dimension. Predominantly it will be moving in the horizontal direction, in the x direction. So, that one dimensional flow is being taken into account. So, we are dealing with one dimensional fluid flow. So, the control surfaces, if you draw it in a three dimensional way, so this is the three dimensional way. So, this particular surface as well as this particular surface, those two surfaces allow the flow inside to the control volume as well as it allows the flow outside the control volume. So, you can now easily find the things here. I can write this particular equation. So, this is section 1 this is section 2. So, the quantities here are V 1, the average velocity across this cross section is V 1 bar, area is A 1 bar. Let us suggest here it is V 2 bar, A 2 bar, depth of flow it is Y 2 here, here it is Y 1 here. So, these things V dot N dA is equal to 0. As this is a dot, you can understand this is a dot product means you are only taking the magnitude. So, I am taking the magnitude of the velocity and that to the average velocity for the entire cross section of the area. So, you know this outward normal vector for this left hand side, it is in the negative direction of the x, whereas for the second section, section 2, the outward normal vector it is in the positive direction. So, V dot n for the section 2 it is a positive quantity, whereas V dot n for the section 1 it is a negative quantity. So, I can write this as V 1 bar A 1 bar plus V 2 bar. Definitely we are not writing A 1 bar like that. V 2 bar A 2 is equal to 0, where V 1 bar is the average velocity in the cross section area A 1, V 2 bar is the average velocity in the cross sectional area A 2. So, what does this mean? V 1 bar A 1 is equal to V 2 bar A 2. So, this is your discharge Q, and as we have already mentioned, the flow is steady. So, the discharge across any cross section it will be same, only that the velocity and the cross sectional area will be different. So, that gives you the continuity equation. If you want to deal with the conservation of momentum equation, so same control volume approach you take. Again, let me write the same equation dB by dt. This is equal to dou by dou t of integral volumetric integral beta rho du plus control surface beta rho v dot n dA. So, I hope you are able to understand du is the integral variable, that is du. We are suggesting that if you integrate du for the entire whichever volume taken into account, that will give you the total volume, all those things. So, now your extensive property is B is equal to m into V actually. So, I can give it in the vectorial form also, it does not matter. Now, if I give it, let us give it in the vectorial form in the beginning, later on we will take the magnitude. Therefore, your beta, small beta will be equal to V. What does this mean? What does this mean? If Reynolds transport equation theorem or Reynolds transport equation meant for the momentum principle, for the momentum quantity. So, if you apply the extensive property as momentum, you will see that the left hand side is the net change in, that is the rate of change of momentum in the control volume. The change of momentum in the control volume, that is equal to the net rate of change of momentum stored inside the control volume plus the outflux, net outflux of momentum or the net momentum flux across the control surfaces of the control volume. So, like this one have to interpret the equation here. According to the physics law, so rate of change in momentum, what is this? This is equal to the net force acting on the control volume. That is the physics law. According to the Newton's law, you can see that rate of change of momentum is equal to net force acting on the control volume. What are the, as we have suggested again, one dimensional flow we are taking into account. We are taking one dimensional flow into account. So, the net force now you have to deal it in the direction of the flow, that is say in the x direction. So, I can give the net force as sigma f x. This is equal to the rate of change of momentum in x direction. With the rate of change of momentum with respect to time in the x direction. Flow is steady. So, if the flow is steady, what does that mean? This particular portion of the equation, it vanishes. So, you will have this is equal to V rho V dot n d. So, the net forces, what are the various forces acting on the control volume that you need to interpret. So, this gives you the net force. So, as we are dealing in the x direction, so we can suggest sigma f x. So, the net force acting the x direction, what are they? Forces due to pressure, gravitational force, and of course, the frictional forces. So, if you recall the uniform flow, there also we have dealt with the same approach. So, the various forces due to pressure, gravitational force, frictional force, all these things you need to take into account.